All right. Hey, welcome, Michelle. My name is Shanshan. I'm a faculty here at the Zhejiang University. It's such a great pleasure to have you come to our 2025 CTI meeting. And it's your second time come back to Hangzhou. Welcome.
Yeah.
How do you
Thank
feel?
you. Oh, I feel great. It feels like coming back to a place. I'm coming back to a place that I know now. I know you. I know many of the team of Huanghei. And so it's a pleasure to be back.
It was such a great talk you're giving this morning, very inspirational.
Yeah,
thank you for sharing with us some of the newest research you do in your lab and truly inspirational. I think we can save that for later. But I want to ask you, you've won so many medals, including the latest one from MIT, the Richard Merkin Medal, and the Berman Medal from Germany. So with so many prizes emphasizing your pioneering work in the CAR T therapy, what do you see that the CAR T therapy has done for the cancer field, and how do you see it going forward in terms of the biggest, most exciting advances you think the field should happen, and the biggest problem the field needs to solve?
Lots of great questions. Our immune system is amazing. Right? It keeps us humans alive on this planet. We have to protect ourselves from, viruses, bacteria, and parasites. And it does an okay job against cancer, but not a perfect job. We know, sadly, so many people die of cancer. It's the second cause of death for humans. So it's good, but it's not perfect. I felt when I was studying to get a PhD in immunology, from what I was learning, that we needed to help our immune system in a new way. Classically, we stimulate the immune system with vaccines. That's great, but that means we stimulate the cells that we already have. How about if we're incapable of fighting something like cancer? What do? Well, we can teach the T cells of our immune system to first identify the cancer and then go on to eliminate it, to kill it. Now that required the design of receptors that we called CARs.
Yes.
It required to figure out methods to introduce the CAR to the T cells. It required identifying suitable targets to reach that goal, and the one we identified is a molecule called CD19.
Yes.
We can talk about it later, maybe.
Yes.
And when we conducted the first clinical trials, they were immediately, remarkably successful. Now, don't think it didn't come easily. For 20 years,
I know.
Everybody was saying, this is a dream, this cannot work, it will never be implemented. So when you ask me, well, what do these prizes mean? It's like so incredible after 20, 25 years, or maybe 30 years of critique. Now people saying, job well done.
And congratulations, sir. That's amazing. And I remember from the morning talk, the beautiful bar graph that you show since the early 2000s, that you first conceived the idea of CAR T, then be able to see the field gradually rise up with all the bars coming to 2020, 2025, with so many clinical trials going on with CAR T, and see this fantastic meeting about cellular therapy. How do you feel about that?
Again, it is a dream come true, although I didn't even dream of all of this. So I can't even say it's a dream come true. It is just amazing. We infused the first CAR T cell patient in June of 2007. And for several years, we couldn't even enroll patients. Most colleagues were critical of this approach. It took a few years until really things got moving. And today, there's a second wave of the use of these CD19 CAR T cells outside of cancer.
That's right.
In autoimmune diseases. And I have to say that China is very much in the lead worldwide in paving the way of the use of CAR T cells in autoimmunity today.
I bet you did not see this happening.
I did not.
In terms of the autoimmune disease and all that.
Well, yes and no.
Maybe that's the reason you choose CD19 over 20.
So let's talk about that.
Okay.
So we chose this molecule back in the 1990s. We had to choose something to work on. And we
Yeah.
thought, well, maybe one day there will be a trial, because those were just experiments. And if it happens, maybe hematological malignancies would be a good choice, because
Right.
T cells can go into the bone marrow.
Right.
It's easier there than some other
Right.
parts of the body. We chose CD19, which was not a well-known molecule. Today, CD19 is a
Right.
little bit of a superstar.
That's right.
But at the time, there was another molecule called CD20. And when I talked to people, they all said, oh, why don't you try CD20?
Yeah.
I said, no.
Obvious choice.
CD19, exactly. CD19 is more abundant. Another reason we chose it is that we were concerned that the body of the patients, if one day they receive these cells, could reject the CAR T cell, make an immune response against the CAR. But if the CAR T cell destroys B cells, maybe the patient cannot make antibodies against the CAR. So we realized that these CARs could be good not just for B cell malignancies, but to eliminate normal B cells that you don't want. But then we didn't do anything about it. And years later, someone in Germany actually tried these CD19 CAR T cells exactly in the way that they had been developed for cancer in autoimmune patients with incredible early, not, we still need to learn more, but incredible outcomes. And as we heard at the meeting this morning, right close by in Shanghai, but also here in Hangzhou, we now have all these trials going on, and I could not.
Very exciting results.
I could not be more excited.
I know. And it sounds like you were thoughtful about choosing CD19 for eliminating B cells, but not exactly for the reason today.
That's right.
But
that's right.
You couldn't be more happy to see more application of the CD19 targeting CAR T.
Absolutely. There are studies today in multiple sclerosis, in neurological disorders, and muscular disorders. So it turns out that CD19 will have, thanks to others, many lives.
Thank you. Thank you for what you do. And so on that topic, I want to ask you, so cancer is heterogeneous, and I think maybe I asked you this before. What do you see the field needs to do to solve the heterogeneous marker of cancer, and what might you could share about what you do in your exciting lab right now on this, big challenge?
Yeah, you're absolutely right. That is a big challenge. Lymphomas and B-cell leukemias were maybe one of the few instances where you could find a cell surface target that would be present in almost every cancer cell. So it was a good choice.
That was,
On the other
very
hand,
smart.
That's not the case for most cancers.
That's
As
right.
you know very well from your research.
Acute leukemia.
You know very well from your own research.
Yes.
Most cancers are very heterogeneous.
Right.
They evolve over time.
Yeah.
And as they evolve, they don't all present the same possible targets. So how can you tackle this? Well, it's probably a combination of targets.
Yes.
And so we have to identify those candidate targets and also figure out how to engineer T cells to target so many molecules. Normally, a T cell can recognize one.
Yeah.
That's what nature does.
Yes.
But now we want to push beyond nature and create T cells that can recognize multiple antigens. That sounds like a logical thing to do, but it's not so easy because it is breaking a law of nature. The law of nature is one T cell recognizes one antigen, and now we want flexibility and multiplicity. So it's a fascinating research challenge, but I think we can find solutions to that.
Cancer is an evolution. I think you're accelerating the evolution of T cells to catching up to beat the cancer. So that's really exciting.
That's a good way of putting it.
Yeah. And I remember the morning talking about the talk you were giving, the CD70, the minor weak expression of CD70 will still be able to tackle by your hit CAR.
Yes.
That was a good example of how you solve the heterogeneity in a certain way, I suppose, right?
You're right, and thank you for bringing that up, because if we have a more sensitive receptor, It means now that we have a broader range of targets to choose from. Until now, we and everybody else have pursued targets that are more abundant. Because they're more abundant, they're probably already known. Because they are more abundant, they're easier for scientists to have discovered in the past. But there's a short list. We need more candidates. And now with these tools, we can look at many, many more molecules that are not as abundant. And that is why I'm more optimistic that we can find combinations of these targets.
That's very true. And maybe I could have the pleasure to ask you the last question. It's going to be a big question. So you must thought a lot about this, the cellular therapy, and how do we think it strategically in terms of engineering the T cells themselves, and maybe in combination with other forms of therapy. So looking to the future, what do you think that the field needs to address in terms of the overarching sort of a challenge of the human health? Where could a cellular therapy apply that you think the most exciting areas to be?
That's not one question. That's multiple questions.
Multiple questions.
But I'm glad that you brought up the question of how to strategically develop this form of medicine. The pharmaceutical industry has very little experience with this. And in fact, cell therapies don't fit. They don't fit the model of creating drugs as has been done for decades. So they have to not only establish new manufacturing methods, but these are cells. They're not molecules, they're not proteins, they're not chemicals. Chemicals and proteins, they're dead, they're inert. Cells are alive. It's what I called years ago living drugs. I said we create living drugs. So the way they are manufactured, distributed, administered is completely new, and there's a lot of learning by the industry, by the hospitals, but also, at least in the West, by insurance companies, how they pay for all of this. So this is challenging the system in many ways.
That's true.
But above all, we need to lower the cost of these. And it's interesting to me that now we conduct some experiments where the goal is not just to solve a biological question, but to lower the cost. But it's essential to do that so that more patients could benefit. It would be a tragedy if these therapies were not fully developed because of economic barriers. We know they can be curative. We know they offer a chance of curing some diseases that are incurable with all other current drugs. But we should not allow the economics to limit their development. So a lot of interesting new directions in this regard.
And do you think the in vivo CAR is going to solve the problem?
It's one idea. There are several ideas. It is possible. For the listeners who don't know, you're referring to an approach where the cells are not taken out of the body from the patient and modified and then re-injected, but where you try to perform the genetic modification inside the body. There are very recently some very exciting results. In fact, there are a few trials in the world, including in China. But the whole safety and efficacy of this is still unknown. So let's see. It's very exciting, and it might be applicable for some diseases or some types of patients, but not others. Let's see where this goes. It's a new adventure in the world of cell therapy.
You remember the chemotherapy era when Dana-Farber was in the basement inventing the chemotherapy for cancer. Nobody believed it's going to take over the world.
That's right.
Then we know 100 years, everything is about chemotherapy. So thank you for what you do, sir, and thank you for your time. Thank you.
Pleasure to talk to you.
Thank you.
Bye-bye.